Hello viewers, welcome back to the course. So, in the last class we have discussed the Fourier series. So, today I am going to start another topic, and that is called the Fourier Integral. So, as we know that the Fourier series is applicable whenever the function f x is a periodic function. So, for the Fourier series I know that the Fourier series is applicable when my function f x is a periodic function. And generally we define my x belongs to from minus L to L. So, in this case we know that our function is a periodic function with period 2L. Now, the thing starts that what will happen when the function f x is not a periodic function. So, in that case suppose I have a function my f x. So, suppose my function is f x and which is not periodic, is not a periodic function. So, what will happen? Because the function is not a periodic function, then I cannot write its Fourier series. So, in that case we generally that if the function is not a periodic, we generally call it that in this case my function f x is treated as a periodic function having whole x axis as a period, as its period. So, in this case we will generally say that okay, the function is periodic and its period is completely the whole real line. So, in that sense I can say that my function is periodic and period of that function is a whole real line. So, in this case now, so to start with the Fourier integral, so I assume that let my f x is a function defined on x axis, that is from minus infinity to infinity, and satisfies the following conditions. The first one is that my function f x is a piecewise function in any finite interval minus L to L. So, this is my first condition, that my function should be a piecewise type in any of the finite interval. The second one is that my function f x is absolutely integrable. As absolutely integrable on the entire x axis. So, what is the meaning of absolutely integral function? It means that my function f x, I take the absolute value and I take the integration from minus infinity to infinity and with respect to x. So, in that case it should be finite. So, if it is happening, then we say that my function is absolutely integrable on the entire x axis. And the third one is, the third condition is that for any x belong to the real line, left and right derivative should exist. So, in this case my function is defined, and for any x I should be able to find its left derivative and the right derivative. So, if all these three conditions are satisfied, then we are able to write the Fourier integral. So, let us see that how we can how we start with the Fourier series, because we know that about the Fourier series, and from the Fourier series I should be able to convert that Fourier series into the Fourier integral. So, let us see that how it happens. So, we know that my Fourier series for the function, so I call it L, because Fourier series I know that it is applicable when the function is periodic. So, I write the Fourier series having the function having the period 2L. So, this is given as a naught plus summation n from 1 to infinity a n cos n pi x by L plus b n sin n pi x by L, where my a naught is, I know that this is equal to the average value of the function dx, and my a n is 1 over L from minus L to L f x cos n pi x by L dx, and my b n in that case is again 1 by L minus L to L f x sin n pi x by L dx. So, this is already we know. Now, what we want to do? We want to find out that what will happen if I take limit L tends to infinity f L x, and this is basically our function, whatever the function we are going to define, because I told you that this function is a periodic function on the entire real line. Okay. So, it has a period as an entire real line. So, this is I am going to do. So, now what do you do? Let us see what will happen. I define a function, the parameter omega is pi by L. So, what is this? Let suppose I take L is equal to pi. In that case my omega will be 1. If I take L is equal to 2 or 2 pi, suppose I take, in that case my omega, for this one my omega will be pi over 2 pi, so half. Okay. When I take my L is equal to pi by 2, in that case my omega will be pi over pi by 2, so that is 2. So, it means it is telling you that how many waves are there from period minus pi to pi. So, in this case when I take L is equal to pi, it shows that there is only one wave from minus pi to pi. When L is equal to 2 pi I am taking, then only half wave is there, and when L is equal to pi by 2 I am taking, then there is a 2 waves. So, we generally call it that W or this omega is a wave number, and if I take for all value of n, then we define omega n as n pi by L. So, this is we call it the nth wave number. Okay. So, after this I can write my function f L x is equal to, so what I do, I put the value of the coefficients here itself, it is minus L to L f x dx plus summation n from 1 to infinity, my a n is this one. So, I will call it 1 over L minus L to L f x cos n pi x by L dx. So, this is I have written there from here, and this is equal to cos n pi x by L. Okay. So, generally I can, because both the x are coming. So, what I do, I will just make it n pi t by L dt, just I change the indexing, plus 1 over L minus L to L f t sin n pi t by L dt, and then I put sin n pi x by L. So, this is the expression and I put my integral there. So, now from here I can write my this factor, I will keep it same. So, this will be here plus, so from here I will try to find out what is my del omega, the change in omega. So, this will be omega n plus 1 minus omega n. So, that will be n plus 1 pi by L minus n pi by L. So, this will give me only pi by L. So, from here I will write that my 1 over L, if I write, so that will be del omega by pi. So, from here I can write my f L x is equal to 1 over 2 L f x dx plus, so instead of 1 over L I will put in this n from 1 to infinity, I will put 1 over pi here, and this is minus L to L f t cos n pi t by L dt into cos. So, instead of n pi, so here I have defined n pi by L. So, I can replace this by cos omega n t, this one, and this one also I can write like this. So, this will be omega n x plus minus L to L f t sin omega n t dt into sin omega n x and the whole del omega. So, this is the expression I got from here. Now, what I do is that, now what I want to do, I want to put what will happen when I take the limit L tends to infinity. So, you know from here that I want to check for this one. So, this is, I consider that this is my function f x, and also I want to check what will happen for del omega. So, del omega is basically limit L tends to infinity, it is pi by L, right. So, from here I can say that this is, so omega del omega is pi by L, and as L tends to infinity, from here I can say that this will goes to d omega, because this is a just for discrete form, and when I put the limit, then my del omega becomes d omega, because when L is very large, this quantity is going to be very small. So, from here now I want to see that what will happen when I apply this limit for each of the term here. So, now let us see that what will happen if I put limit L tends to infinity to this integral, the first integral minus L to L f x dx. So, basically it become, this is same as this one, minus infinity to infinity f x dx. Now, we know from here, we know that any integral f x is less than mod of dx. So, this we already know, right. So, from here, and this is true for any integration. And what is this? So, this is already in the condition I have started with, that my function is absolutely integrable. It means this value is a finite value. Like for example, I take a function, I define a function f x is equal to suppose 1 when it is less than equal to 1, 0 otherwise. So, in this case I want to check whether this function is a absolute integrable or not. So, I can take my limit from minus infinity to infinity f x mod x dx, and this is basically from minus 1 to 1, 1 into dx. So, that is a finite value. So, I can say that this function is absolute integrable. So, I know that this is the condition I started with, and this is equal to finite. So, from here I can say that the limit L tends to infinity 1 over 2 L minus L to L f x dx become 0, because this quantity is finite and divided by the infinity, L tends to infinity. So, this becomes 0. So, from here I can say that the first integral will be my 0. Then I start with the second one. Now, what will happen? So, now I put the limit. So, left side I will get f x, and on the right hand side what I will get? I will get first integral is 0. So, from here I can find my pi from here. Then I will get n from 1 to infinity, and this quantity can be written as minus infinity. So, minus L to L f t cos omega n t dt cos omega n x plus minus L to L f t sin omega n t dt sin omega n x, and the whole this one is del omega. But I just now we have done that when the L tends to infinity, this del omega becomes the d omega. So, from here I can write my expression as f x is equal to, and if you see this one, this is same as the Riemann sum of the sum integrable quantity. So, if I put the L tends to infinity, then this sum will tends to become the integral from 0 to infinity, because this is coming from n is equal to 1, 2, 3, 4. So, this summation become integrable from 0 to infinity, and from here I can write that this become equal to 1 over epsilon 1 over pi, and then I can write this expression as from 0 to infinity, and the inside quantity will be same. So, this is minus infinity to infinity f of t. So, omega n becomes omega in that case dt into cos omega x plus minus infinity to infinity f t sin omega t dt into sin omega x and the integration with respect to d omega. So, this is my complete expression for this one. So, from here what I do that I write this integral as, because if you see this one, if I do the integration with respect to t, in that case I will get the function of omega. So, I write this as a omega, some function omega, and I write this quantity as b omega. So, from here I can write my expression is 1 over pi from 0 to infinity a omega cos omega x plus b omega sin omega x d omega. So, this is the integral I am getting where my a omega is minus infinity to infinity f of t into cos omega t dt, and b omega is minus infinity to infinity f t sin omega t dt. So, this expression, whatever the expression is written here, is called Fourier integral defined for the function f x, and this function satisfy all the three condition whatever that I have written in the starting. So, if my function is satisfying all the condition, then the corresponding Fourier integral can be written like this one, where these are my coefficients a omega and b omega. So, this is called the Fourier integral. So, let us do one example that how we can write the solve this one. Now, so I want to write, so before that I just want to start with some case also. So, let us do one some cases as we have done for the Fourier series. The case one I take that if the function f x is an even function in the whole domain, that is f of minus x is equal to f x. So, what will happen in that case? I know that if the function f x is a even function, then the expression a omega is equal to minus infinity to infinity f of t I have written, you can write x also, no problem now, cos of omega t dt in this case. Now, this is also even function and this is also the even function. So, it is an even function. So, from here I can write that this is equal to 2 times 0 to infinity f of t cos omega t dt, and in that case my b omega will be from minus infinity to infinity f t sin omega t dt, and this is the odd function and this is the even function, the product is the odd function. So, this is equal to 0. So, in that case, so from here I can say that the coefficient will be 0, and then my Fourier integral will be 1 over pi from 0 to infinity a omega cos omega x d omega. So, this will be there with a omega is equal to 2 times 0 to infinity f of t cos omega t dt. So, this is called, so this expression is called cosine Fourier integral. So, this is similar as the Fourier cosine series. The case 2, when my function f x is an odd function. So, in that case my function, I can write my function is equal to minus of f x, and you know that from there I can show that my a omega will be 0 in that case, and my b omega will be 2 times from 0 to infinity f of t sin omega t dt, and then my corresponding Fourier integral will be 1 over pi 0 to infinity b omega sin omega x d omega, and is called sin Fourier integral or Fourier sine integral, sine integral. So, this is the cases when your function is either a even function or the odd function. So, let us do some examples. So, let us take one example. So, I take my function f x is equal to, so this is a function I started with. So, I just take the same function 1 when mod x is less than equal to 1 and 0 otherwise. So, if you see this function is like this one. So, this is my x axis, this is 0 and this is x axis, this is my y axis I am taking. So, the function from -1 to 1. So, this is -1 and this is 1. So, in that case my function is 1 and after that this is 0. So, it is satisfying whether I want to check whether it is satisfying all the three conditions or not. So, first condition is that this function is a piecewise continuous, yeah it is a piecewise continuous function from -1 to 1. So, that is true. Second one is that I want to check whether this function is a integrable or not, absolute integrable, and we know that this is absolute integral that we have done. And third one is that at each value of x the left derivative and the right derivative should exist. So, here also we can see that the left derivative and the right derivative existing, left derivative and right derivative from -1 and left derivative and right derivative the x equal to 1, it is exists there and all other value it will exist. So, from here I can say that f x satisfy all the conditions for the Fourier integral. So, from here I want to find this Fourier integral. Now, if you see from here, what will happen if I take f equal to -x? You can see from here that this function is like this. So, it is a, if you see that it is a even function because in this case it is same as f x. So, from here I can say that this function f x is an even function because the value of the function at x from greater than 0 and the value of the function at x less than 0 are the same, just the image about the y axis. So, from here if I want to write my Fourier integral, so my Fourier integral for this function will be 1 over pi a omega cos omega x d omega, and from here I can find my a omega. So, a omega is 2 times from 0 to infinity f of t cos omega t, and I can write my dt. So, this is equal to 2, and from 0 to infinity or does not matter in this case I can also take from 0 to infinity. My f t from 0 to infinity is what? It is just the function 1 into cos omega t dt. So, this from here I can write, and this is the sin omega t by omega 2 times from 0 to infinity. because if I take the derivative of sin omega t is the cos omega t. So, from here I can write this is equal to sin infinity minus sin 0. No, not infinity, from 0 to 1. So, this quantity I can define, this one is from 0 to 1, otherwise it is value 0. So, this is equal to this sin omega t over omega 0 to 1. So, from here I can take my quantity as sin omega minus 0. So, this will be 2 times sin omega over omega. So, that is my a omega. So, from here after finding the value of a omega, I can define my Fourier cosine integral will be 1 over pi 0 to infinity. A omega is this one, 2 times sin omega over omega into cos omega x d omega. So, this will be d omega. So, which can further be solved. So, it will be 2 over pi sin omega cos omega x by omega d omega. So, this is my Fourier cosine integral for the function, which function I have taken. So, this is the solution for the problem. So, this further it can further be solved. So, that is you can do yourself. So, after doing this one, now I will define the another form. So, let us do complex form of the Fourier integral. So, I want to write the complex form of the Fourier integral. So, all the conditions are same. Now, I know that if a function is a non-periodic function and defined from minus infinity to infinity and satisfying all these conditions, then I know that my Fourier integral is this one from 0 to infinity, and then so instead of a omega I just write it expression here. So, from here I can write from minus infinity to infinity f of t cos omega t dt into cos omega x d omega plus minus infinity to infinity f of t sin omega t dt sin omega x d omega. So, this is the expression for the Fourier integral. Now, what I do is that from here I can write this expression as 1 over pi from 0 to infinity. So, I will keep all the terms together. So, from here I can write this expression can be written as cos omega t into cos omega x plus sin omega t into sin omega x, okay, into dt d omega. So, this is the quantity left with. So, from here I can write this expression So, from here I can write, so what is this? So, if I write cos A plus B, so the expression is cos A cos B plus sin A sin B. So, from here I will write this quantity as, so this is minus sign, cos A minus B, cos A cos B plus sin A sin B. So, from here I can put this quantity here. So, I can write this expression as a cos x minus t into omega dt d omega. So, this quantity can be written like this one. Okay. So, from here, so this expression, the expression I have written is this become this quantity. Now, from here if you see that, if you see from here that if I am doing this integration with respect to t here first, and after doing the integration putting the limits, this expression is a function, some value, some constant into the cos of x minus t omega, and which is the even function. So, from here I can say that this expression, the whole expression is an even function, is an even function in omega. So, from here I can write this quantity as, so this is the even function with respect to omega, and then I am taking the integration from 0 to infinity with respect to omega. So, from here I can write this expression as from minus infinity to infinity, and inside the expression will be same f t cos x minus t omega dt d omega, and this will be 2 times. So, this becomes, so I can write this as 2 pi, because here I am taking from minus infinity to infinity, otherwise earlier it was from 0 to infinity. So, I have written this expression as this one. So, this is what I have written. So, here the expression for that become this one. Now, what I do is that from here I can say that I will take the quantity like this one, minus infinity to infinity f t sin x minus t omega dt d omega. So, I know that the same terminology or the same will be used here, because in that case the function is the odd function in omega. So, if I do the integration from minus infinity to infinity of the odd function, then I know that this quantity will be 0. So, from here I can say that this quantity is 0. So, what I do? So, I take this quantity as equation number 1 and 2, then I add together. So, what I do that I write f x is equal to 1 over 2 pi f t cos x minus t omega dt plus I time, I is the complex number, I write this expression minus infinity to infinity f t sin x minus t omega dt, and the whole expression d omega, because I know that this quantity taking the integral from minus infinity to infinity is 0. So, I can just add this one 0 quantity on the both side plus I, the complex number I am taking. So, from here my f x will be 1 over 2 pi, this quantity I am taking, and this quantity I will write minus infinity to infinity f of t, this quantity is there, and this expression will be cos x minus t omega plus I times sin x minus t omega dt, and the whole d omega. So, I will get this expression, and this quantity, if I want to write its Euler form in the complex way in the complex form, a complex number, this will be equal to e raised to power I x minus t omega. So, from here I can say that my function f x will be 1 over 2 pi minus infinity to infinity f of t e raised to power I x minus t omega dt, and the whole expression can be written as d omega. So, after doing this one, what I do is that now I separate this integral. So, I just instead of 1 over 2 pi, I write 1 over under root 2 pi, and I put this minus infinity to infinity here, and I put 1 over 2 pi here, under root 2 pi minus infinity to infinity here. So, inside I will take this value minus I t omega dt, and I will get here I x omega d omega, because I have separated this expression e raised to power I x minus t omega. So, I will write this one as e raised to power minus I t omega inside with respect to t, and e raised to power I x omega with respect to the outer integral. From here I will write this quantity as f x is equal to 1 over 2 pi under root 2 pi from minus infinity to infinity, and I call it a f of omega e I x omega d omega. So, this expression I have written here, where I call this expression minus infinity to infinity 1 over under 2 pi, so f t is there. So, it will be f t e raised to power minus I omega t dt. So, this expression I call it f hat omega, and we call it capital F of f t. So, this is called Fourier transform, and from the Fourier transform, if I take the Fourier transform, because I am taking the transform of the function f t and the expression is coming in the terms of omega. So, it is called the Fourier transform of the function f x, and this then we call it inverse Fourier transform. Why we call it inverse Fourier transform? Because after getting the Fourier transform, see, this is the initially I have the function in x, and then this space will move from the x to the frequency space, that the omega, and from omega I am going back to the x space. So, that is why if this is the Fourier transform, then I call it the inverse Fourier transform. So, this is the expression, and Now, after defining this Fourier transform, if you see from this expression, I remember that we have also done the Laplace transformations. In the earlier lectures, we have done the Laplace transformation. So, in that case also I have defined the Laplace transformation for the function f t. So, I call it Laplace function of the function f t. If you remember, it was from 0 to infinity f t e raised to power minus s t dt, and we call it f of s. So, in that case I start with the function f t. After doing the integration, this convert to the S space. So, in this case, this is my Laplace transformation. So, if you just compare this with the Fourier transform, you will see that instead of S, if I put I omega here in this expression and outside it will be 1 over under root 2 pi, then it becomes the Fourier transform. So, instead of S, I just take the complex number I omega. Then the Laplace transformation can be converted into the Fourier, but only thing is that the Fourier transform is valid from minus infinity to infinity and the Laplace transformation was from 0 to infinity. So, just to remember that sometimes we want to remember the Fourier transform. So, if you already know the Laplace transform, then instead of S you just put I omega from minus infinity to infinity and multiply by 1 over under root 2 pi. So, this is called the Fourier transform of the function. So, this is very important concept of the Fourier transform, that we have the function which is given to me in terms of the physical space, we call it the t or x space, and I convert that physical space into the frequency space. So, this is my frequency space, and once I am able to get the function in the frequency space, and suppose I want to go back to the physical space, then we define the inverse Fourier transform, because this facility was not there in the Laplace transformation. In the Laplace transformation, if you remember that we know the Laplace transformation, but there was no mathematical expression for the inverse Laplace transformation. But in the Fourier case, we have the Fourier transformation as well as the expression for the inverse Fourier transformation. So, now, after doing this one, so like we had some sufficient condition for the Laplace transformation to be there for the function, then the same way I can define the sufficient conditions for the existence of Fourier transform. Fourier transform for a function f x. So, what are the sufficient condition for the existence of the Fourier transform of the function? So, the condition one is that, so your function f x is well defined from minus infinity to infinity. So, first is that the same condition, the f x is piecewise continuous on every interval from minus L to L. So, this is there, and the second one is that f x is absolute integrable on the whole domain from minus infinity to infinity. And the third condition is same as that left and right hand derivative exist. at each x left and right hand derivative exist. So, if these three conditions are there, so in fact, if the three conditions are satisfied, then I can define my Fourier integral, and from there we have seen that we have found the expression for Fourier transform. So, if this is the sufficient condition that I choose a function and satisfying all these three conditions, then its Fourier transform will always exist. So, let us do one example. So, the same example I am taking, because I know that this example is satisfying all the conditions. So, I will take this one. So, this is my expression. So, I know that this function satisfies all these three conditions. Then I want to find its Fourier transform. So, in this case I want to write the Fourier transform. So, I will write f of f x and I will call it f hat omega. So, this will be equal to 1 over under root 2 pi from minus infinity to infinity. So, this is my function I am applying f x into e raised to power minus I omega x, and that is dx. So, this one I will write. So, from here I can write my expression. So, now I put the value of the function, and here my function is defined from minus 1 to 1. So, and the value is 1. So, it will be e raised to power minus I omega x dx. So, if I solve this, so it will be under root 2 pi. So, this will be e raised to power minus I omega x divided by minus I omega and the limit minus 1 to 1. So, from here I can write as under root pi I omega, and inside quantity will be e raised to power minus I omega 1 minus e raised to power minus minus plus I omega, and this iota I can take on the as a numerator. So, this will be I multiply and divide by I. So, I square will be minus 1. So, from here I can write my expression will be I over under root 2 pi omega into e minus I omega minus e I omega. So, that is my Fourier transform for my function. So, this is equal to I under root pi omega So, this quantity is the Fourier transform of the function here. Now, from here I can define one quantity that is called the magnitude, the amplitude spectrum. So, from here I define another quantity, amplitude spectrum. So, what is the amplitude spectrum? The graph of omega, because this function is in terms of omega, and modulus value of f omega, the corresponding Fourier transform. So, if I plot this one is called the amplitude spectrum of the function f t, and omega is called the frequency of the spectrum. So, based on this one, once I get the expression for, like here I am getting the expression for the f hat omega, then I can plot for a different value of omega, and then whatever the expression I get, that is called the frequency spectrum. Now, once I know the Fourier transform, then I will start with the properties. So, properties of the Fourier transform. So, if you remember that when we started with the Laplace transform, after that we also discussed all the properties, that how it behaves for different function, what are the properties. So, the same way I can define the properties of the Fourier transform. So, the first property is linearity. So, for the linearity I can say that Fourier transform satisfy the linearity property. Or I can say that Fourier transform then I can say the Fourier transform is a linear transform. So, let us do the proof for this. So, proof is very simple. So, I take, so we will take let us take two functions f of t and g of t, and these both function f t and g t satisfying all the sufficient condition, that both are piecewise continuous, absolutely integrable, and the third condition also satisfied. So, then we can define, so let we take the two function whose Fourier transform is well defined. So, well defined means I write its Fourier transform of the function f t as omega, and for another one we call it g omega. So, these are the corresponding Fourier transform. Now, I want to take Fourier transform of the function, some constant I take a of f t plus b of g t. So, this one I want to define. So, from here I can say that this is equal to 1 over under 2 pi from minus infinity to infinity e raised to power minus I omega t dt. And now I know that the integral is a linear function. So, from here I can write a of f t e of minus I omega t dt. So, this is the expression we have taken. and from here I can write that this is can be written as 1 over under 2 pi, taking the constant a outside. So, inside I will get f t e raised to minus I omega t dt plus b over under 2 pi g t e raised to minus I omega t dt. So, this quantity can be written as, and what about this one? So, this is I can write as the a times into f of omega. So, this is the corresponding Fourier transform of the function f t, and this can be written as b times g hat omega. So, from here I can write that this is equal to a Fourier transform of the function f t plus b Fourier transform b into Fourier transform of the function g t. So, this is the expression we got. So, from here we can say that it satisfies the linear property. So, today we will stop here. So, in the today class we have started with the Fourier integral, and then using the expression for Fourier integral, then with the help of some mathematical expression we able to define the Fourier transform. In the next class we will go further and try to solve using the Fourier transform, we try to solve some differential equation. So, thank you very much for viewing this. Thanks a lot.